Morning everyone, this is Zhenyi from Tsinghua University. Today my topic is the design of digital demodulation circuit for closed-loop control of MEMS gyroscopes. Now first of all, let's say what is the MEMS gyro. It is a sensor that measures the angle or rate of rotation, and it is designed or manufactured under MEMS process. A MEMS gyro is widely used in many fields such as military defense, like unmanned aerial vehicle, industrial robots, games, and vehicle navigation, like the gyro in your mobile phones. And in general, it has small size, high integration, and low cost. And now let's see the Gyro Discussed today. The right picture shows the gyro developed by our laboratory. It is a resonant MEMS gyroscope, and its working principle is the Coriolis effect. And it can be represented by a second-order mass spring damping system. And under the action of the driving force, usually the driving force is an electrostatic force with a sinusoid form. The mass produces a resonant motion in the driving axis. And now if an angular velocity is generated perpendicular to the XOY plane, another Coriolis effect will be generated in the detection axis, and now the mass will produce a resonant motion in the detection axis. And the equation in the brown square box shows the dynamic equation for the drive axis and the detection axis. By solving the two equations, we can obtain the simplified mathematical model of the displacement of the mass in the drive axis or detection axis. And the two equations can be united to one equation, which is shown in the right square box. And from the equation, you can say the signal from the drive axis or detection axis can be represented by the in-phase component with related to the signal with a cosine form, and the orthogonal component with a signal related with sinusoid form. And now let's see what we need to do. The equation established above is under the two conditions. One is the signal from the drive axis will be stable. That is to say, the signal from the drive axis should have a constant amplitude and a constant phase. Usually the phase should be a zero. Another we need to do is to prevent the motion coupling between the two axes. Let's think about it. The Coriolis force causes the mass produce a resonant motion in the detection axis, and the motion from the detection axis will cause another Coriolis force in the drive axis. If we do nothing, the motion from the two axes will fail to establish the equation mentioned above. So that's the two things we need to do. And before we do the loop control of the two axes, we need to calculate the amplitude and the phase of the signals. Let's see how to calculate the amplitude and phase. The scheme is based on the least mean square algorithm, and it is implemented with a digital circuit with higher execution efficiency, real-time performance, higher integration. For the signal with simplified mathematical model, the circuit deals with iterative expression. Typically speaking, this algorithm is commonly used in signal processing. So let's move on to some details about the implementation. This is the data path of the demodulation circuit, and the input signals are two reference signals and one sampled signal. All the signals are quantized by a 32-bit fixed point number, and the data range is from -1 to 1. In addition, the reference signals are generated by the coding algorithm. Let's see the simulation results. The first picture shows the coding algorithm. This module generates the sine and cosine waves, and the next picture shows the simulation of the least mean square demodulation circuit. In this simulation, the input signal is a standard sine wave, and the amplitude is set to 0.5 and the phase is set to 0. After demodulation, we can see the signal from the drive axis or detection axis, and converge, and the values obtained after multiplying with a constant value are consistent with the preset value. After that, we can get the entire solution for the auto loop control. Let's take the drive loop control as an example. The aim of the loop control in the drive axis is to keep the signal from the drive axis a standard sine wave. That is to say, we need to keep the amplitude constant and the phase to be zero. In this picture, the signal from the drive axis are sent to the listening square demodulation module, and this module outputs two signals. One is the in-phase component, and the other is the orthogonal component. And take the in-phase component as an example. This is related to the phase of the amplitude of the drive axis signal of the drive signal. And this component was sent to a PI controller, and the controller outputs a gain factor to adjust the values of the driving voltage. That will finish a loop control for the amplitude of the drive axis. The detection loop control, the working principle is almost the same as the drive loop control. What is different is the aim. The aim for the detection loop control is to keep the signal from the detection axis to be a zero, to avoid the motion coupling. Now let's see some information about the implementation on an FPGA. This experiment was carried out in a prototype verification board with the MCU and FPGA. The Gyro was established using a programming language in the MCU, and the circuit is implemented on the FPGA. The left bottom is a picture for the portion view of the raised transfer level, and the results are presented here. And the two pictures show the signals of the drive axis and the detection axis in time domain and frequency domain. From the picture, we can see the signals from the drive axis after some time have become stable, and it's typically a standard sine wave. And the signal from the detection axis after some time is near zero. Now let's make a summary. First, we implement a signal demodulation and loop control in a digital circuit, and it provides a solution for potential improvement on system integration, power cost, speed, area. And typically speaking, it is an application-specific integrated circuit implemented on an FPGA for more flexibility, higher integration, and lower power consumption. A system on a chip and a standard CMOS process will be a good choice, and this is what I want to show you in the end. About our current focus, the three pictures show the architecture, the layout, and the die of the system on chip. It is a digital analog hybrid associated with an application-specific module. The module is what I have described before, and it was shipped out and a CMOS process, and the area is less than 81 square millimeters. It provides a solution for a system in packaging in our lab, and other parameters like power consumption and total performance, like precision, these parameters remain to be measured. And if you are interested in it, welcome to discuss and communicate with us. And here are some references. Thank you for your attention.